Okay, let's start by going, or well, I write down the previous work, which, I mean, as I got such distracted for the meeting, it's actually probably the preparation that I can do for copying this. Okay, maybe on the meta note, let me quickly write this down because it seems kind of important. Eating preparation. Setting up everything required for a session takes probably 10 minutes. And I need to do a bunch of things, which are not even written down in the setup. Create a new section in the Google document. It actually takes also a minute, I guess. Well, maybe less. I need to set up the Google documents. I need to recall what was done previously. And I could do that without the other person, I think. At least sort of, well, then would still be good to talk with the other person about it. But, yeah, okay, let me write that. Read the notes from the previous meeting with that person. Think about generally what are all the active projects right now. There's also a thing about SFF. Yes, wait, I forgot when the deadline is for SFF. And the problem is you need some sort of sponsor to give reply to SFF. And the only sponsor I reached out is Ashgrow, and they didn't answer at all so far. Except that they said, oh, I guess our website form doesn't work.
Okay.
So maybe... Yeah, okay, let's read what we did before. Okay, there is, for example, general, let me write down in general. General is formalizing Matteo's algorithm. Getting the hull tiling algorithm, which is what we were doing. Graph matching notation. Yeah, and then, well, I guess there's sort of also on the meta level, there's like, this is on the object level, and then there's like applying for a grant, which in some sense, by formalizing Matteo's algorithm and tiling algorithm, that's actually about the grants. And the graph matching notation is just a thing that I was doing on my own about what I ended up doing when I thought what is the best research thing if I don't think about the grant to do. So probably want to just write the whole tiling algorithm. I think we are like, it's probably like over 80% done. In terms of we know the steps, and then I guess would be about explaining it. So it seems like if we can finish the Heil tiling algorithm and then have some posts, it's like, look here, we made this algorithm. That would be good for a grant. I'm not quite sure how. Well, it's a lot better than having not something like that. Not sure if that's enough. But that's what would probably be the best thing to do for a grant. So I guess we want to do that.
Sounds good.
So I will check. Okay, so you probably want to copy. I will copy this section about the algorithm to the current document. Okay.
Alright.
That took really long.
No problem. There's a lot in this document.
Yeah, so probably that's, I can write this down as also a thing to do before a meeting. To move the documents. Okay, so if you want to continue work on this algorithm, I think we want to... Okay, probably it makes sense to just walk through the algorithm on the whiteboards to see how far we are, sort of, I guess.
Mm-hmm. I think I remember where, like, you and I left off last time, but I don't know if that's exactly where you need to pick up right now.
Okay, where is
What?
that? Yes,
I think we got through talking about, well, basically down to the heading computing graph isomorphism with world deltas. Right? We were like, yeah, we were talking about the thing where, if you label...
Wait, I think we were significantly
edges.
further, no?
Did we?
Yes, I think that was
Oh, sorry,
the first thing
We got
when we worked on
through
it.
through this section. Yeah. Yeah, I remember all of the... I don't know if you can see where I am, but yes.
And let's see. Now I see where you are.
Yeah, we talked through this algorithm for sure.
Yeah, I think... Or, well, right now I just need to degrime my whiteboard.
Okay.
But I think in the moment, which you could already do is like I would just reread these like algorithm steps and to remember what we have. Maybe it makes even more sense to immediately draw it on the whiteboard.
Yeah, that makes sense to me. Whatever you think.
Okay, so let's just walk through the initial thing. So the first thing we do, so we give an arbitrary graph. And then we say select some vertex in this graph. And from this graph vertex we do BFS. And this BFS is to determine the starting points for later steps of the algorithm. So we like I guess we could make it slightly more precise, this step, by saying, okay, how do we... So like, do something like pair iterations or something. Let's write the type of this. It's like you get a graph. The starting vertex. And then, depending how we write it, if we just write it, if we were to write it in Haskell, if it was lazy, we could say it's a list of pairs of vertices. That's sort of the first step what we're doing. We are like creating sort of this infinite list of just sort of for the later steps of the algorithm to have like this list of pairs.
Okay.
And we do it with the like BFS pairs, we could call this. Okay, wait, so like this doesn't make sense to you because I didn't really explain what this does.
I don't know what it does yet. Yeah.
It's just the first step of the algorithm we wrote down, which is like do the BFS to get pairs of vertices.
Yes.
Okay, so basically like it would be like, okay, well, we get just the starting vertex. Okay, we can't do any pairs. Now do BFS step 1. Now we get this, and this.
Mm-hmm.
Now make all pairs of this. So the Cartesian product.
3 pairs of. Yep.
Well, no, 9 pairs. Wait, 9 pairs? No, wait, what? Yes, 9 pairs. You get 9 pairs.
Sorry, pairs. Pairs of all 4, not just the things in the next layer.
Yes.
Yeah. Okay.
Cartesian product of. Basically, what we want to do is, okay, basically this is a way to like this is a way to iterate the Cartesian product. Like if we have a graph G, then we could be like G dot vertices squared. To get all pairs of vertices.
Are pairs ordered?
Yes.
Got it.
We don't care about the ordering though. But
we don't get, like, is AB a different pair than BA?
Yeah, but we don't care about it here. So I guess you could say it's a set.
So what are the 9? I'm sorry. I really want to understand this step.
But 9 ordered pairs, we don't care about sort of all of them, I think, for the algorithm.
Right. Okay.
But yes, that's an optimization you could do later. Just don't do the double things.
Yeah.
Um,
Okay, got it.
yeah, this is really terrible computational. Wait, is it? So this is a major question, I think. How terrible because I think this is maybe a step where the performance like makes the algorithm just not work or something. But I'm not sure about it because, well, if you just think about the pairs, it will be like n squared for n being the number of vertices. Number of vertices squared like pairs, and for each of these we do some other step of the algorithm. So that's like still polynomial, right? I think. Polynomial time complexity.
Yeah, it seems like it. I don't know. I don't feel confident. But yeah, you're just like adding. Linear is not exactly the right word, but
It's definitely not
um,
linear.
yeah. But it's not like
But it's not like
ballooning in
2
a
to the
crazy
number of
way.
vertices.
Yeah, right, exactly. Yeah.
Or is it? One, two, 3, 4, 5, 6, 7, 8, 9. Wait, this maybe 2 to the n. So, I mean, we have like, we start with one starting vertex, and now we have 3. Start with this, we have 3. Start with this, we have 3. Start with this, we have 3. Possibilities for the second one. And we have 3 plus 3 plus 3 plus 3. So 4 times 3. Is it not 12
Yeah.
possible pairs? This would be 16.
But I still I feel like I'm still missing something about how we're about what we're calling pairs. You're saying it one step further than what you've colored in, you get to 16?
No, I'm saying 2 to the
No.
fourth 16. And I'm
Oh,
wondering,
okay, yeah.
and
If
here,
it
but
were
here we
to,
have 4 to 4 times 3, I think.
yeah.
Is that right? 4 times 3?
For which set of nodes are we at 4
For all
times 3?
pairs. We have so many, this many pairs. Because you
In the
can
colored in
choose
one?
this for the first thing, and
Yep.
then the second one could be any of these. Well, I guess it could be this, but this definitely want to exclude that. But I guess for now we could also think about this times 4, and then it would be 4 to the power of 2, and then it would be Wait, but it's also 16, what?
Yeah, I guess if you can pick yourself, then it's 16. Like if a node can be paired with itself, but is that a thing that we want?
So if you have 5
Yep.
nodes, then it would be 5 squared. So it is n
Again,
squared.
if you can pick yourself.
Yes, let's assume that, because like for the complexity it doesn't matter. There's like one.
Okay.
We exclude
Yeah.
one thing.
Yeah. So if
That's,
you could choose yourself, and we don't care about repeating pairs in a different order, then it is just n squared. Right? It's like any set of things, and you pair each of them with every member of the set. That's squaring. That's right.
So if we were to think of the permutations, then it would be exponential, because then we would have n to the n.
Permutations.
Well, like all n tuples. Like here, if you think about this, then like all 4 tuples,
Yep.
4 elements, then it would be exponentially many in the number of vertices. But now it is not exponentially number of vertices. That's just a constant because of the tuples, I guess. And here we would have sort of 25 if we have 5 to the 2. But if we would have 2 to the 5, that would be 32. Okay, so then would grow larger. So 10 to the 2 is 100, but 2 to the 10 is 2, 4, 8, 16, 32,
1024.
1, 2, 8, 2, 5, 6, 5. Yes. Okay. Okay, so yes, so I guess it's not exponential. Okay, so this first step is we get these pairs, and we sort of, well, the thing is, and this thing is sort of like, basically we think about this, we want to evaluate all pairs in a vertex, but no, actually it's important that we don't just think of all pairs. We want to think of all pairs that are sort of locally expanded. We iterate them, and we start from some starting vertex, and then we sort of expand this with the BFS, and then we consider all these new pairs that we can do with the BFS. That's actually important, that we don't just, because there will be some step in the algorithm where it's like, yes, now I found like the local thing I'm looking for, like some repeating structure, and we want that to be as small as possible, sort of, the repeating structure. Or there will be some sort of condition check, and we wanted that this condition check is true for the smallest sort of, the pairs which are closest together, sort of. Okay. Okay, that's the first step in the algorithm, to compute the pairs. Well, I mean, it's actually like, it's not really the first step, it's the first kind of thing we need, but we would like, the rest of the algorithm would be in a loop in that, iterating over that. Okay, and then we just consider the vertices. And then we get, okay, then we get the graphs from the pairs. So now we have the pairs, and then what we do with that is we have another function, induce BFS graph, which takes in graph, vertex in the graph, and the depth. And then it returns us another graph, which is the subgraph of the original graph. And we call this on these pairs. And then we check, are they equal? Structure equal. And this is not how you write this. Graph. Well, it takes two graphs and tells us whether they have the same structure. It's like this isomorphic thing, sort of.
Mm-hmm.
Okay, and then what is written here is we check if it is tiling. This is maybe actually not required. So yes, that's okay. That's the first version of the algorithm, I guess. I will omit this tiling step. Okay. I think so. The question now is, how do we So, well, here I say the structure is equal, but it's actually not what we want exactly. This is want something much more specific. So, well, okay, let's look at it over here. So here we have this graph which is tiling. This is also a graph. And the red vertices, they are sort of, well, here the red vertices, they are sort of, we have these tiles and sort of vertices can be the same between tiles. By which I mean what do I mean by that? It is a question. But like this blue vertex here is not the same position sort of as the red vertex, right?
Mm-hmm.
So we want to find all the red vertices, because then we know sort of, well, then we are sort of consistent, right? Then we are like, I have this repeating structure, and if I sort of labeled stuff like this, if in the repeating structure we have like some A, some B, some C, some D, I want to make it such that I find sort of, I'm sort of somewhere in some starting vertex, that's some of these, right? Because every vertex is actually sort of in this replacement graph.
Mm-hmm.
If I select any vertex, it will be in this replacement graph, which is this graph that we use, and where we like have some lattice and we replace every vertex in lattice with this replacement graph. So we select any vertex, will be some vertex in this replacement graph. Now I want to find sort of in the adjacent replacement graphs that I have also got, the vertex. That is the same label sort of, but we don't have the labels actually in this graph.
Right.
So, well, or, okay, let's see. Because I think if we had that, then I think I know the rest of the algorithm, or very close. Because we would do then is sort of, we are just calculating the path between this red and this red, 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 and then we are sort of done. Because like we could do something like this. Then the idea would be that what we can do is, yes, we don't really need this. So, well, if we have this graph again. And we had these vertices. We magically computed them somehow. What we can do now is because the next thing we need, which actually we also need to compute, is sort of the path. That's like this, the shortest path that reaches these other vertices, such that we pass through all of these vertices. Like this, these vertices are important, right? These, not vertices, these edges are important because these edges are going between the things. And well, if you think about sort of this graph, well, right now we're thinking basically about the problem where we know it's like some n-dimensional lattice, and that means we have two n edges that are going out and going in the replacement graph. Or like in an undirected graph, there would be like two n edges, right?
Right.
So that means what we can do now is we can do the thing where we have all of these paths, and then we can sort of remove them from the graph, and now we can like do a BFS from here, and then see whether the BFS terminates. So if we have just removed all of these edges, then it will terminate, right?
Oh,
because
yeah.
I removed all of these edges.
Yep.
And then what we do is we sort of like give more edges. Then we're like, okay, what if I add this edge in? What happens now? The BFS again. It's like, oh, now it goes here, then it goes here, or like it goes here, and then it goes here, and then it goes here, and here, and then it goes on forever. So now this was not the right edge. So this edge we need to keep removed. And then we do the same thing for the other edges. It's like, oh, add this edge. Oh, well, okay, actually it still terminates. Remove this edge, still terminates. And then we do that. And then like we can like go to exactly this tiling thing.
Yeah, that's very cool.
Actually, we might find not exactly the tiling thing, but like, well, we will find a tiling thing that can be tiled to lattice. But it might be that there are just multiple things that can be tiled into lattice.
Sure. Yep. Yeah.
And then there's also some way to infer, I think, the dimensionality of the lattice, such that we know when we have found enough edges, I think. But probably can also do some other check. Yeah, I think you could then verify that that's correct. Okay, but the question is, how do we get these vertices? That would be one setup. And that was sort of related, or kind of, well, that's what I thought was maybe exactly what the graph isomorphism is for. Because these edges are sort of guaranteed to have the same structure.
Yeah.
Not sure actually, the graph isomorphism, how I solved it was by assuming we have edge labels with the deltas, which you could have in a world state graph. I'm not actually sure this is required at all.
Yeah, what would change if you didn't have them?
Then the graph isomorphism is NP hard then, I think. But I'm somewhat confused. Maybe I would need to ask GPT. Let me do that really quickly. Tell me about the graph isomorphism problem. I heard that is NP hard. That is assuming that we don't have edge labels, right? If we had vertex labels, this wouldn't make the problem that much easier because we are by default assuming that in the graph we can compare vertices, right?
Interesting.
Wait, it doesn't simplify the problem?
Well, it doesn't if you're just like the labels you're adding are the world state transformation things, right? Which is like adding additional information.
But GPT thinks a bit weird about this because, maybe this is a standard graph isomorphism problem. What about the problem where we want to find the isomorphism, but we define the isomorphism such that the edge labels also need to be equal? Then the problem would be easier, right? It would not be the standard isomorphism problem though. Yeah. So the thing is, you have actually multiple things. We also have, well, okay, let's see what GPT thinks. But it's like, I'm considering a graph isomorphism problem where we have a conditional constraint. Specifically, we know the starting vertex and that this vertex needs to be sort of equal to the starting vertex in the other graph. Yeah, I'm not sure if that was a good explanation. Aha. Because that we definitely know. We definitely have a starting vertex. Yeah, maybe we ask GPT about structure detection algorithms. What algorithms exist to discover repeating structures in a graph? So I'm pretty sure there exists some of them. For the first algorithm, do we then try to figure out graph isomorphism or solve some other problem? Huh. Okay, they use heuristics. We are not actually trying to do a heuristic algorithm right now, though. So I think... So what's the intermediate step that's missing from this algorithm we're talking about? There's something about how we find these points. And what was done before is basically these points are the ones that are isomorphic, right? This has the same structure as this one, as this one. This graph's actually a bit weird because every vertex is isomorphic to every other vertex if we don't do some additional thing, I think. Because every vertex has... Or that might be slightly wrong. I guess I'm somewhat confused about it, but like this vertex... No, I think it is right. I think every vertex has the same structure, right? If I select this vertex, well, if I rotate this entire graph 90 degrees, they're sort of the same graph, right? It's exactly the same thing.
The graph definitely stays the same if you rotate it, but not every vertex could take the place of every other. Like they're not all.
No, that's what
right.
I mean, though. Or what I mean is, you rotate the graph, and if you don't compare vertices, sort of, well, if you just look at the embedding will also be exactly the same. I guess I'm somewhat confused what I mean. It stays the same if you rotate it. Like, I'm saying, like, if we look at this vertex and we do BFS, the BFS of any step will be the same as if I do BFS here or here or here or here. Any vertex has exactly the same BFS. I'm assuming it's infinite, this graph. So any vertex will always be exactly the same For like the
Yeah.
BFS graph will exactly be the same. Okay, yes, that's the problem.
Yeah, that's right.
Okay, let me write it in a Google Doc. So basically, consider the following graph. If we pick any vertex and do a BFS search to induce a graph, this graph will in some sense always be this graph will always have exactly the same structure, no matter which. So we can't really detect. So we can't detect the violet circled vertices via simple structural equality. We need to do something like we need to do something else. I mean, this is sort of, in some graphs it will actually just work. Or
Yeah, it's like it just happens to be the case about this graph that it's totally like isomorphic throughout. But you could draw graphs that aren't that way.
yeah, but I guess ideally we want the algorithm to work for this graph also.
Yeah, yeah.
I think we can do it maybe by checking if the vertices are equal. Like, let's see. So in this specific graph, what we can do is like if I do BFS of this vertex of size 2, I would get this graph. Right, this would be for the size of 1, and this would be search of size 2, of depth 2. Okay, let's do it for a different vertex. Well, obviously it's exactly the same. Right? If I rotate this, sort of, then it would be the graph I would draw for this vertex. But the thing is, I think we could do something like, well, okay, let's imagine we do it for the other graph. So we would get this, or that's the graph I would get, which is the same.
Yep.
But now we can do like, we could like sort of color vertices that are the same. Or like, well, yes. So for example, this vertex is the same as this vertex. Right, that's an operation we can do. Well, assuming we can compare if two vertices are equal.
Mm-hmm.
So we know if two vertices are the same.
Yeah.
And well, this is the same as this vertex. So we could sort of compute that there's a lot of overlap between these vertices, I think.
Yeah.
And I think maybe this is somehow can be used to solve this problem. Like this is almost like sort of, there's lots of overlap between these two graphs.
Yes.
And if we were to select this graph over here, it would be a lot less overlap. And I feel like maybe somehow this could be used.
Mm-hmm.
This is not the overlap, it's only 3 vertices. If we are thinking about this is the graph that's sort of to the left, it's from this vertex.
Mm-hmm.
The problem is, how do we stop? Because if I just go further to the right, like take this vertex that's further to the right, it will even be like has 0 overlap now. Maybe we want to do something different about checking whether it tiles or something. Okay. So here's the thing. Maybe, but one thing we could do is iterate through these kinds of graphs. Like in the beginning, we might maybe have like this graph, and then it would be like, look, this graph is like the same structure as this other graph. So let's do this procedure here, where we cut the edges and then see whether we stop leaking, sort of. But then if we like, oh yes, this is a graph that we don't leak, sort of the BFS, it stops at some point. Then we don't stop, we continue and we find the next sort of vertex that's structurally the same and do this.
Yeah.
And we continue doing that until we find something where we do leak. or something. Like the sort of the largest thing where we can stop leaking. But I think, does this work?
How do you know when you've found the largest? Like if you go on and you just like keep going. I don't know. Are you
Well,
guaranteed to like ever find a stopping point?
well, the idea would be that I guess the problem is you would also leak here. The idea was that if you detect that you're leaking the BFS, if it's not finite, if it doesn't terminate, then you know that sort of you must have now, but it means that you're passing between the lattices, right? Otherwise,
Yes.
it wouldn't happen. But the thing about this is that if I just remove this edge, I'm still making it infinite. So I know that, so I actually know that this edge is, do I know that? I definitely know that this edge makes the search infinite. And if I remove it, then it's not infinite, I guess. That's what I know. Maybe we could do something much simpler, where we just start at the vertex, and we now do BFS and see if it gets infinite. And if it does, we check which edge is responsible for making it infinite. And then we try to grow it as large as possible without making it infinite. But
I guess I'm curious how algorithmically you check whether something is going infinite.
You just do it and we see does it stop.
Yeah, but like when do you decide you've checked enough? Like how do you know it won't eventually stop?
Well, and in the other algorithm version that I had, then you could sort of do things like, if lattice is like this dimensionality, because I got to some evidence that tells me what's the dimensionality, then I know there can be only this many edges, so I must make it
once
finite.
You've gone beyond that.
Yeah.
Yeah.
And I guess you also want to check how does it tile. Like maybe like because we're actually not thinking about this at all so far. Maybe we want to actually think about how we check if the graph tiles efficiently, and then maybe this approach was a bit wrong because it was very specialized. But if we had this function that checks if the graph tiles, it would actually be trivial to get sort of the tiling graph probably. Like then you would just be like BFS, or like just try some permutations or something. Like some simple version of the algorithm would just be like to try like things and then check this all the time, and then you will get it at some point. Which was probably be not that efficient, but then it would sort of just work, kind of. And then how you would make this efficient is sort of like calculate what makes it not tile or something. And then sort of adjust that. And then you could definitely infer some model that tiles. And that seems, I don't know. Maybe this is a better thing to focus on. Okay, and this other thing was like, try to find sets of edges such that the BFS does still terminate. Then try to increase these edges further and further, and try to find the largest graph for which it doesn't terminate. But while somehow excluding the possibility that the graph just grows forever and we cut the edges at some further away place. Maybe we could exclude this because if we sort of expand the graph a lot further beyond just one tile, then we would need to cut many more edges in order to make the BFS terminate. Okay, we'll go to the toilet. Okay, I think it's easy maybe to check if it tiles. You only need to have the function that constructs, well, so here's what we could do. So you have this like graph that we sort of, so we're given some graph, and now we're wondering, does this graph tile? Or like, oh no, what did I do? So we can have this algorithm for constructing a graph, and that algorithm is basically just sort of, we could imagine something like this. You're given a graph, which is the replacement graph. You're given, I guess we don't know the dimensionality of the lattice. So we could iterate through dimensionality, which is so kind of bad. But okay, sort of the very dumb algorithm that's very inefficient for checking whether the graph tiles is just give me a graph, give me the replacement graph, because this is the like base graph, and then like, well, okay, then give me the mapping. Oh no, then we would need to iterate through the mapping. That's so inefficient. So we could have this function, which is just a function that replaces all the vertices in the base graph with the replacement graph and connects the edges of the base graph's vertex with like edges according to this function. So if we were to just iterate through all of the parameters of this, only having this one fixed, it would tell us whether, then we could get some graph and we compare if that graph is the same as this graph that we start with, and then tells us if it tiles it.
Yep.
So now what we can do is well, for this we just use lattice graphs of dimensionality 1, 2, 3, 4, 5. I guess the edge map, that is a bit, that's sort of the problem, because like iterating through the lattices is like, It's not that bad, I guess, if you don't have a really high dimensional lattice. But here you would need to try all possible mappings between vertices. Like wait, but we can just infer it. Actually, it's not a problem, I think. Because I think if we just do BFS on this, like we do select arbitrary vertex, do BFS, or like, well, do we do BFS? Well, I guess I'm imagining something like pick a vertex, now add sort of an edge, or like do BFS. Wait, do BFS. Like I'm imagining sort of that you could read off. Like you have the BFS, and then I have like these vertices, like maybe I got this thing. And now I can sort of like say, oh, the maps must be such that this edge over here, and this edge over here, and this edge over these edges here, like these must be the edges that are sort of mapping, right? Like these are the edges these must be the edges of the lattice that I'm mapping into, sort of. Okay, that was very confusing what I said. Like these are the edges
just
from
the last
this map.
part. Yeah. Uh-huh.
Like this is the edge such that if I have the lattice, let's say, and this have like 4 edges, I mean, in this case doesn't make sense. Actually, in this case, wait, 1, 2, 3, 4, 5, 6. Okay, no, it's even. Wait, 6, even 2. Yes, that would mean wait, but that is so weird, because this means this would be a 3-dimensional lattice now. Cannot be a 2-dimensional lattice.
What makes it that way?
So we are inferring this kind of lattice. Yes. Mm-hmm. Well, I mean, because it's 6 incoming edges.
Okay. Oh, I see. Yeah. If you're, yeah.
So this actually now allows us to determine this parameter. And this also allows us to determine this parameter somehow, though, but a bit more complicatedly probably. Because like,
why do we need to conceptualize something? Sorry. Why do we need to conceptualize something with 6 connections as 3-dimensional rather than just like a spider in 2-dimensional space?
Well, a lattice graph in 2 dimensions is this.
Is always for. I see. Yeah. So if something has 6 connections, if you're making it a lattice, it's 3-dimensional. Yeah. That makes sense.
Yeah, 6. So if you make it 3-dimensional, then it's always 6. If it was 5, then we would know it is no lattice. This doesn't make sense, because there is no lattice with 5, unless you have maybe at the edge or something.
Cool.
So 6 connection axis tells us 3D lattice. And it also tells us how to map things for the map function here, I think. Because it must be that this edge is a lattice edge. So if we have the lattice, which is here, this edge, for example, like it must be that this edge is this edge. So I guess it doesn't tell us like how exactly do they map in the lattice. Like it might be that this edge is this edge, or it might be this other edge. And I guess we kind of need to. Do we need to know that? I think we kind of need to sort of try all the possibilities of these 6 edges. And check whether it then tiles the lattice. Is that right? So we need to do something like this. We have this thing, and now we need to try. So now we could sort of try the connections that are possible. So we're sort of assuming, I mean, this is kind of wrong. It's not the simplest steps, but we're assuming this is a vertex now. And we're wondering how we connect these edges up. So we could say like, yes, okay, I will connect them up such that this is sort of going here.
Mm-hmm.
But it could also be, another possibility could be that this is going, I guess, over here. Wait, would that make sense? Certainly some of these possibilities can be excluded, or it's my intuition. Okay, I'm very confused now.
Okay, I mean, I see what you're doing, and we're wondering whether. I mean, what is the question you're trying to answer? Those are both ways of, I guess, tiling the thing.
Well, are they?
Or are they? That's the question, isn't it? Yeah.
So here would connect to this thing.
Yeah. And then it would connect again.
Like, is these like all like? I mean, so I have this blob, and now I could decide sort of. So the edge that goes up in the blob, where does it map to in the blob itself, sort of, right?
Exactly. Yeah.
And then I can place it there. And now if I do the next up edge, I could place it again there. So that would mean if I go up, I'm always going, well, I'm entering the blob again, but it's not determined. So I could write it in a different way. We can write it like this. And now we just do like, so this, for example, we could write it as.
Yep.
And so now the question, so I can just do this. This is one possible thing. Well, what about then I can do another thing. Like, oh yeah, this goes here, and this goes still here.
Right. And those are both valid ways of like tiling this shape.
But yeah, so that's also my intuition. Why is this? So, I mean, no matter where we go out, we always get into the same lattice. I mean, but therefore, well, not the same lattice, but the. So if I go up, I will always go to the bottom vertex, sort of there. So like to the vertex that has the down connection. So that is sort of regular. If I go diagonally down to the left, I will always end up at the vertex that is up to the right, has the up to the left connection, I mean. And well, like if I go here, I will go here. I drew it as directional arrows, but this is actually what be sort of undirectional.
Mm-hmm.
So it feels like this would be then tiling, I guess, because always same. But these are all different ways to tile it, right? It's like,
Yes.
and only one would describe the original graph, I think. Is that correct?
Only one way of tiling it would describe the original graph.
Well, if I were to say, like imagine this was the original graph. I mean, this would actually be the original graph, sort of. Well, I'm confused because now it's 6-dimensional. I mean, 3-dimensional. But this is different from this, right? If I do a BFS, then here's a vertex with 2 connections, and then a vertex with 3 connections.
Mm-hmm.
Wait,
I
but
guess
this
I'm
is
curious
the same.
If they both are in a sense 2-dimensional representations of the 3-dimensional lattice, then they, like, in 3-dimensional space just must be the same, or like isomorphic to each other, right? Like, because there's only one lattice graph.
Well, the lattice is the same. The lattice is the same,
Yeah.
but
Yeah.
But that is only what once we contract these, once we see this as single vertices. But what's not the same is like I'm going from here.
Mm-hmm.
Wait, is it even? Wait, this graph has always still the property that there are 3 edges, right, everywhere, for every vertex.
Yeah.
I think this is just sort of wrong. I don't know. like somehow I feel like, or like what, I guess I can understand what you were saying. But the mere fact that this is a 6-dimensional lattice instead of a 3-dimensional lattice instead of a 2-dimensional lattice should be like, yes, this is obviously wrong. This is because like this infers the 6-dimensional lattice, but the original was the 3-dimensional lattice. But the original is a 2-dimensional lattice, and therefore like it doesn't make any sense basically. If you actually do the BFS search, if you induce a graph with BFS, the structure of this graph will be different from the structure of the original. Actually, we can detect that. Yes, okay, actually we can detect that, therefore we can exclude this possibility.
Okay.
So okay, that seems important. So note that if we do generate a subgraph via BFS, we could get this graph. This graph, I'm writing this in the Google Doc. We can draw a vertex around the subgraph. Not a vertex. Cutting off the edges that we would get at the next step of the BFS. These edges need to be now the edges that connect the different vertices of the lattice. Note how we have 6 outgoing edges, which would mean that our lattice is 3-dimensional. Note how the original lattice was 2-dimensional, meaning it had 4 outgoing edges. It seems this implies that if we do a BFS on a graph constructed with this BFS subgraph, we would get a different structure that we could detect as different. By doing a BFS search in the tiling graph and doing a graph isomorphism comparison. This means we can compute that this subgraph is not the correct replacement graph. Following are all the possible ways in which different The following show 2 ways in which these lattice graph level edges could be connected up. using the function of this type, we can then tile this graph in particular ways like the following two. Okay. Okay. Now at least this gives us a method to compute whether what we did did make any sense. Okay, this is very difficult. Thought it would be much easier to compute the replacement graph. Also, I guess if you want to go in 10 minutes, so we could like do reflection now.
Yeah, that makes sense. I guess I'm also curious to do the thing that we've talked about sometimes of like, in the best case scenario, how would the thing we did today help us solve alignment? Like which piece of the path are we at from here to we got a solved problem?
It's a good question. So we have the world state graph thing. Well, or like I'm not sure. Well, world state graph is a program, kind of. Mm-hmm. Any world state graph represents a program. Any program has a world state graph. Well, this specific kind of program where we have the ask agent function, which determines then the structure of the graph. If we sort of think of the ask agent function could return anything, then it's like this game tree. It's like, oh, we could do action A, action B, and then we would get to different state in the world. Mm-hmm. So this is about the world state graph is representing the possibilities of how the agent can steer the world into particular states. That is like just a graph. So what we're doing right now is we're doing a bunch of different things. I mean, there are a bunch of different things. So like we could think about like, okay, we have the world state graph, but it's way too large. How do we compress it? Or how do we make the world state graph abstracted? Or I'm not quite sure what I mean with abstract, but like what we're doing right now, that would be about the world state graph has some structure in it, which is the lattice kind of structure, but it's at a higher level. We get it if we sort of merge some vertices in a particular way. Mm-hmm. And so if the environment is exactly like this kind of graph we were thinking about, where we have a lattice graph that's replaced with some graph and then connected in a consistent way, then we could infer the structure and then we get a lattice, and then the lattice is good because it's like really simple and you can do some algorithms on it that you couldn't do otherwise. And this is sort of a general thing that you could do probably with other kinds of structures, and we were trying to figure out how we would do it in the simplest kind of structure of a lattice. Because this basically corresponds to like a particular kind of world modeling operation. If you want to construct a model of the world, you would be like, aha, mm-hmm. I want to detect if we have this kind of lattice structure, because this lattice structure allows you to like run some algorithms that are nice, because it's the simplest kind of structure. So if the graph that describes the world currently, or some subpart of the world, can be like made into this lattice structure, then we would like to do that, because then we can reason about the world much better. So
Yep.
that's what we did, I guess. Trying to figure out, for this very specific kind of structure, how would you go about discovering it and modeling it, such that then you can like do algorithms on it that would be better, like planning algorithms that, like you can always do BFS, but then you could do like maybe some smarter algorithms, or like not smarter, but like algorithms that only work if you have a certain kind of structure, like lattice structure. Does that make sense?
Yeah, that makes sense. Cool.
Yes, that's good to remind oneself of. So this is actually about how to build a model of the world, which is probably very unobvious if the talking, well, it's very easy to forget if you're just thinking of graphs, and then it's like, here's some random graph, how can we do this really abstract operation on it?
Yeah, exactly. Cool. Okay, so
figure out how to build a model of the world in a way that we understand how that thing works. That's the thing we're trying to do.
Yeah. Cool. Yeah, do you have any thoughts about how today went? How you feel?
I was very tired in the beginning. For some reason now I'm not tired at all.
That's good.
Yes, I think I'm probably now addicted to some medication for sleep apnea, because I didn't take it. And now then I was really tired. So I guess now I need to take it. Always. But I only took it like 3 times, so it's so weird.
Yeah.
So that was probably the main reason. What was it? Well, there was really a bit weird this session, I think, or I don't quite understand why. Okay, here's one weird thing which I don't understand, which is like, when we started, I thought we basically had the algorithm figured out, but then we got really confused about how to do anything.
Yeah.
Or I'm not sure.
I think I found that's not an uncommon thing when I go to try to explain something to somebody else. I like realize that there were gaps or like shorthand in my own internal understanding that like need to be fleshed out. So I don't know if that's exactly what you're describing, but
so
that's
I think
one of the really valuable things about like needing to explain something to someone else.
Yeah, I think probably it was like the special case of the graph, which is structurally identical for any BFS on any vertex, is the thing we didn't consider at all before.
Yeah.
And that makes things break.
Right.
And it feels like maybe we could have be better before at noticing things like that. I feel like maybe, yes, I think it would be good to have a sort of specific thing of like, let's try to break this or something. Let's try to figure out how this thing we're doing fails. I think we're not doing that enough.
Okay.
somehow we need to have a setup where we red team our own thing that we had so far.
Yeah, that seems good.
But I don't know how to integrate this. Maybe something like each time we finish writing, or like I wrote something in a Google document, or like one section or something, before doing sort of the next thing, we want to break it. Or maybe maybe this is not even exactly the issue. So one thing is, like, when writing this algorithm, we wrote lists of very high-level instructions.
Mm-hmm.
Somehow we lost this feature that we would get if we write more low-level pseudocode, that we wouldn't be able to write down the pseudocode at all if we didn't understand something. Now it's possible to write something down even though you don't quite understand how you would actually do it. So maybe so another thing, therefore, might be something like, when you write one step of the algorithm, at a high level, before moving on to the next step, try to unroll it into a lower level version of pseudocode. Oh, another thing is also, like, we didn't write down the type signatures. Actually, I think maybe that wasn't really a problem, but it seems like in general it would be better if you wrote down the type signatures for the algorithm.
Mm-hmm.
So we want to, after each no, I don't know maybe I want to set up some sort of alarm, red teaming alarm. And that would then be about, just let's try to break everything.
Yeah.
Or at least,
Seems like a good thing to do.
For some reason it's really unnatural to do this, which is really, or yeah, I think definitely you can overdo this. I'm not quite sure when you want to do what, but I'm pretty sure we're doing it not enough because we're not doing it really at all. Set up an alarm for red teaming, but you try to break your own things.
Mm-hmm.
And try to write lower level code at least to the point where you feel confident that you could write it. Always write down the type signatures. And to red team things, probably the best thing to do is, like, because I did the red team accidentally, actually. I was like, here's a graph. Talk about with somebody else, like, here's a graph, and then it's like, yeah, see this graph, and then they are like, wait, this graph doesn't work though. Oh, yes.
Right.
So try to come up with concrete examples where the thing you're thinking about would not work anymore. So like come up with counterexamples, yes.
Exactly. Okay, I should go.
Mm-hmm.
But those all seem like really good takeaways to me.
Nice.